As a student, especially during your first years of studies, you might have become accustomed to having access to correct answers or even correct solutions to problems. In more advanced studies, and indeed when you start working after your graduation, you will have to get used to having no such answers or solutions. Thus, you need to learn strategies for critically evaluating if your solution is reasonable or not. Here, I want to talk about 5 different strategies that might help you save points on exams and perhaps even prevent a disaster once you work as an engineer. 1. Drawing on your own experience. 2. Learning by heart the magnitude of some characteristics and/or phenomena. 3. Calculating intermediate results that can be interpreted. 4. Unit analysis. 5. Sign errors. So let's go through these one by one. 1. Drawing on your own experience. As a beginner, it's often difficult to draw on your own experience. As you work as an engineer, you will, over the years, collect more and more experience in your specific field, such that you may, for example, have a feeling of how large the heat exchanger needs to be in an evaporator, or how large a distillation column needs to be. However, already as a student, it might pay off to at least try to compare your calculations with things you have experienced yourself. If you calculated the required volume of a reactor, that is to produce tons of some substance every day, and its volume is about the same as the volume of your bag, then clearly something seems to be wrong. Don't expect to be good at this from the start, but to become good at something, we need to train doing that thing. 2. Learning by heart the magnitude of some characteristics and/or phenomena. For many of us, there is a limit to how much information we can learn by heart. Still, if you know that gas diffusivity is typically somewhere around 10 to the power of -5 square meters per second, you should suspect that something is wrong if you calculate a gas diffusivity to be 100 times smaller. Similarly, if you know approximately how much electricity is produced per year in your country, around 150 terawatt hours in Sweden, and you calculate the electricity demand for a factory or a process to be larger than that, you should suspect that you did a mistake somewhere. 3. Calculating intermediate results that can be interpreted. Quite often, the calculations that you need to carry out as an engineer may be rather long and complicated. So why wait until you have calculated your final answer until you check that you seem to be on the right track? I once had a student who on an exam calculated the diffusivity of a substance in a gas to a ridiculously small value, many orders of magnitude smaller than what is reasonable. He realized that something was wrong and wrote a comment about that on his exam. I never asked how pressed for time he was at the exam, but the problem in his solution strategy was that he did not calculate any intermediate results. In the task I gave at the exam, the students first had to estimate how large the molecule was and then use that to estimate the diffusivity. This student never actually calculated the size of the molecule, but instead combined that equation with the equation for estimating diffusivity. When I corrected his exam, I carried out that calculation and noted that with his numbers, the diameter of the molecule was approximately the same as the size of our solar system. Clearly a ridiculously large value. I cannot be sure, but I would suspect that the odds are rather good that he would have identified his mistake if he had had time to check if the estimated size of the molecule was reasonable. Thus, if you have time on your written exam to calculate intermediate results that you can check if they are reasonable, do that. One very simple example is that if you are to calculate an average, the result should not be larger than the largest individual value or smaller than the smallest individual value, right? This is true regardless of what kind of average you are taking, and there are several kinds of averages. I have lost count of how many times I've had to deduct points for averages calculated that are clearly not an average. 4. Unit analysis. Analyzing your units is another good strategy. Some units are a bit trickier to deal with than others. I, for one, always have difficulties in remembering how to express Pascal in the base SI units, and I usually grab for the nearest handbook or computer when I need to do that. For more tips on unit analysis, see the separate video on unit analysis. Link below. 5. Sign errors. Finally, sign errors creep up now and then in student answers on exams, and it is important to learn to interpret these errors. If you, for example, have calculated the diffusive transport from point A to point B as a negative number, you might simply have defined the positive direction in the wrong way, and your numerical answer might still be okay. If you, on the other hand, have calculated the flux through a membrane and get a negative value, chances are that there either is something seriously wrong with your calculation, or that the answer simply is there is no flux through the membrane, since the transmembrane pressure is too low.